Now let's take just a couple of minutes to explore a few interesting applications of what we've been studying in Chapter 11. We can now use energy to find out what minimum velocity we would need to actually fire a projectile into air and send it out into orbit, or even look beyond orbit. For example, what if we wanted to fire something off of the surface of the Earth, blast it off of here, and have it just never ever return again, escape orbit, escape the planet? Now, here are initial values. Let's say that we didn't know the initial velocity. We're actually looking for that. So that would actually be our question mark here. We would know that we'd be beginning our object at a position 1 Earth radius away from the center of the planet, or the center of mass here. And our final values, once it has actually gone up here and escaped, the final values would be it has reached a final velocity of 0 and a final position of our max. So when we look at the initial side of our energy equation, that the initial energy better be equal to the final because energy should be conserved. When we look at that, we'd start out with a 1/2 mv squared. We would also have a negative gmm over an r, where that r is the radius of Earth. So we're starting out with that potential energy. And at the end, we end with all potential energy, negative gmm over r max. Now, when we arrange this, we'd find that these little masses of whatever it is that we're blasting off the planet, those all cancel out. And we could solve for v sub I, where we'd multiply all this stuff over here by a 2, and they have this gmm in common there. So you end up with this 2 gmm multiplied by 1 over the Earth radius minus 1 over r max. Now, if the initial speed was known, you could plug that in and maybe find out what this R max would actually be. What kind of altitude could you blast something up to based on a known initial velocity? But if you were looking at what we call escape speed would be looking at the point where R max now becomes infinity. It never has to return to Earth. And if this becomes an infinity down here, really this 1 over infinity just means you're going to 0. So you ultimately could then replace this or simplify this as the escape speed being equal to the square roots of 2gm over r. And this would be of whatever thing you are trying to escape. So if you're trying to escape Earth, you'd put in the mass and radius of Earth. If you were trying to escape the sun, you would put in the mass and radius of the sun. Now notice how this equation is independent of the object's mass that's being projected away. So whatever it is that we're shooting off the planet, the mass of that thing doesn't matter, which means we could be talking about a gigantic spacecraft, or we could be talking about a single molecule of nitrogen. And each of these will have the exact same escape speed because their mass does not matter. It's also independent of the direction of the velocity. So we could be shooting it up this way, but we could also be shooting the object kind of like this. It doesn't really make a difference which way you shoot that. It would be independent of that direction. This equation can be applied to any planet, like I said, with a known mass and radius, and we could plug those in. In fact, if you look at table 11.2 in your books, you'd find escape speeds for different planets and the sun. What you'd see there is that Pluto is about 1.1 kilometers per second to escape, whereas the sun is actually 618 kilometers per second to escape. If we were to look at Earth ends up being about 11.2 kilometers per second to escape the Earth's gravitational pull. What's interesting about this is that this actually explains why we see the type of atmosphere that we have on the Earth that we do. Because the escape speed for Earth is 11.2 kilometers per second, heavier things like nitrogen and oxygen, they aren't moving fast enough to escape, so they are stuck to us, and they basically become a part of our atmosphere. But hydrogen, on the other hand, which is actually the most abundant element in the entire universe, is not found in abundance in the Earth's atmosphere. And the reason for that is because hydrogen is moving at a speed that is greater than our escape speed. It can get away, and it doesn't have to be bound to the planet. Another really interesting application to look at would be black holes. Now remember, we briefly discussed the idea of a supernova, where you have this explosion of a very massive star. And in that explosion, the mass of that star now begins to collapse. Now, if that core mass is less than, this is going the wrong way, is less than 1.4 times the mass of the sun, that collapsed core will probably just sort of cool down and become a white dwarf star, just another type of star. But if that core mass is greater than 1.4 times the mass of the sun, it will likely create the neutron star that we talked about. Basically, because that mass is so great, under its own gravitational forces, this thing begins to collapse even further. And these neutron stars are these amazing stars because they take the entire mass of a star, but they collapse it down into a radius of only about 10 kilometers. Now, this is ridiculously dense to the point where about 1 teaspoon of this material, if you had it on Earth, would actually weigh 5 billion tons. So you're taking an entire star and collapsing it into a radius of 10 kilometers. An amazing thing. However, if you take a core mass that is greater than 3 solar masses, or 3 times the mass of the sun, that collapse could continue even further and actually continue to the point where it becomes a very, very small, dense object that we call a black hole. A black hole is basically the remains of stars that have collapsed under their own gravitational forces. And that pull from gravity is so strong that objects cannot escape. Now remember, on the last slide, we saw that that escape speed was proportional to the gravitational constant and the mass and radius of whatever it was that you were trying to escape. So it depends on m and r. Now, for a black hole, it is so dense in terms of that mass and that radius that the escape speed, this v over here, actually ends up being faster than the speed of light, which is essentially the universal speed limit. Nothing moves faster than the speed of light. So even light cannot escape a black hole, which is, of course, why they would call it black. Now, the Schwarzschild radius might be something that you have heard of, or the event horizon is another term that they have for that, but that's really just this imaginary surface of a sphere with a critical radius r where the escape speed would be c, or the speed of light. So if this here was your actual black hole, we could draw sort of an imaginary surface around this, or a horizon around this, and say at this place, if you got this close to the black hole, this is where light would actually be able to escape. Any closer than that, and even light is not going to be able to escape this thing. So the event horizon is really the limit of how close you can come to that black hole with any sort of hope of possibly escaping. You'd have to be moving at the speed of light to be able to get away from this thing if you got that close at the Schwarzschild radius or at the event horizon. Now, although light from the black hole itself cannot escape and therefore cannot be seen, light from events around the black hole actually can be visible. What you see in the other diagram that we have here is what they call an accretion disk. What's happening is a star is near this black hole, and the black hole's intense gravitational pull is actually pulling material off of the star and into the black hole. And as that material is being pulled into the black hole, you can see the events from around this and actually creating this accretion disk. This is one of the ways that they identify black holes when they're looking for them out in the universe. So a pretty interesting application of what we've studied in Chapter 11.